Hello there. If you're having trouble falling asleep, I'm gonna go ramble on and solve a physics problem, and it may help you fall asleep. So here's the problem. Let's say we've got a plank of wood. Gotta move that plank of wood down here so you can see it. There we go, we got a plank of wood. Okay, and we define a point in the center, and we call that point P. Boom. That's point P. The length of this plank of wood is L, and it has a mass of M. Okay, we've got a plank of wood. Mass M, length L, with a point P in the center. And the question is to calculate the moment of inertia relative to point P. So, find moment of inertia. Now, if you don't know what a moment of inertia is, that doesn't matter. It'll still help you fall asleep listening to me talk about it. Okay, so we're going to find the moment of inertia. First thing is we need to note, this is another given in the problem, that we have evenly distributed mass. So, evenly distributed mass. Okay. What does that mean, evenly distributed? It means that it has the same mass density across this entire plank of wood. So, it's got a linear mass density of the entire mass divided by the length. What does that mean? It means that if you take a piece of that wood, a smaller piece of that wood of a certain length, in order to figure out how much mass is in that smaller piece, you take that length of the piece of wood, multiply it by this linear mass density, and that gives you the total mass of that piece of wood. We're going to use that later. Okay, now let's find the moment of inertia. To start, let's go to the definition of the moment of inertia relative to the point P. So what you do is you sum over all of the pieces of mass. Here's it's going to be a continuous sum, so we have an integral. All of the mass of this plank of wood. And what are we going to sum? The position of that mass relative to the point P squared times the piece of mass, amount of mass. That's our definition. Okay, so now let's plug things in to be able to calculate this, because it's hard to calculate an integral that just says all mass. We need to replace it with some actual numerical limits of integration. And also dm here, since if we want to integrate, we've got two variables here. We've got r and we've got m. If we want to make this easier, we want to have everything in terms of one variable, so we can just do normal integral here. So the first thing to do would be to write dm in terms of r, so that everything here is in terms of r. Well, dm, as we integrate and we're a certain distance r away from the center, or center point, we are looking at that dm there is talking about a tiny little piece of mass, dm. That's our little dm. So I guess the question is, how much mass is in that dm? Of this we call dr, a small increment of r, dr. We can then calculate using our linear density that we have over here. We can calculate the amount of mass in that small little bit of mass, dm. So I'm going to do that over here. I'm just going to put like a little side calculation. So I put up the brackets to say it's like a side calculation. Side calc. Side calculation. Well, dm in terms of r, we'd write dm is equal to dr, that small little length over here, times the linear mass density. And that'll give us the total amount of mass in that little area over there. We can also rewrite this as dr times m over L. I'm going to use this lambda here all the way until the end of the calculation because it's just less to write. Okay, so we've done our side calculation. We also need to take a look, do another like little side calculation here. We also need to figure out what limits of integration. We're going to be integrating over r. Right now we have, here, you know what, I'll write out what we have in the integral for the moment. We've got all mass. Okay, and we can write r squared, and then we can plug in what we got, dr times lambda dr. Okay, now what do we do for these limits of integration? Well, if we're doing everything, r is the distance from the piece of the mass to the center. Well, it means we want to start all the way from this end, and we want to move all to the other end. We'll start all the way from the left, move all the way to the right. So if you're in the center, the distance all the way to the left from the center would be minus L over 2. And then if we go to the other side, it would be plus L over 2. So we can continue over here and write in the limits of integration from minus L over 2 to L over 2. Notice we can take this lambda here and take it out of the integral because it's a constant, because it's evenly distributed. It's the same everywhere in the plank of wood. And we're left with r squared dr. Okay. Now we just do the integral. Okay, so it's an r integral over r squared, so that turns into r over 3. R to the third over 3 minus L over 2 all the way to L over 2. We can plug this in. We get L over 2 to the third all over 3 minus L over 2 all the way to the third divided by 3. Now, this minus here we can pull out of the parentheses, out of that, because we've got an odd number here. When we pull out the parentheses, we get a minus minus, so this turns into plus. You end up with, right, is lambda L over 3. Oh, I'm leaving a frame. Let's go look around here. Right here, lambda L over 3 all that third over 3 minus. Oh, well, we said that this minus goes with that minus to make a plus. Plus here. Plus L over 3 to the third. Sorry, over 2. Mistake. Divided by 3. pieces of the same thing added together, you get 2 times that. So you get lambda times 2/3. And now let's multiply. Let's write it like this. L over 2 to the third. We can write this as L to the third over 2 to the third. So lambda times 2/3 times L to the third over 2 to the third is 8. I'm just going to write it like this, 2 to the third, because then we can easily show how we can cancel that out. And that takes us down here. Almost done with the problem. What do we have? We've got lambda. We've got a 3 here. We've got 2 squared, that's a 4. So 3 times 4 is 12. So we've got lambda 1 over 12 times L. 2 and then let's plug in what we have for lambda finally, so we can get back into the quantities given in the problem, which is L. M over L 1/12 L to the third. Can cancel out one of these L's, so it turns into L squared. And it turns into 1/12. This is in total 1/12 n squared. So that's the moment of inertia relative to the center of wood. Doesn't have to work in a rigid body. It's just a line like this. Work relative to the center. Boom. Now at this point, you're probably asleep, or if you're not, probably more sleepy than you were before. That's the hope. The podcast that I've listened to in the past, it's a guy who just kind of rambles on about all sorts of things to help you fall asleep. I found that sometimes it made me sleepier, but sometimes it made me laugh, and that kept me up. So I think doing a physics problem that's not funny enough, it's boring enough, to help you fall asleep.